As you can see, lesson 2, it's a really big lesson. It's not sort of equivalent to lesson 1 in terms of time and effort. I think I've possibly gone a little bit over the top with the explanations, but I am aware that you've left college, and a lot of you, well, almost all of you, won't have the year 2 textbook. You've just got the year 1 textbook. So I've tried to cover all the bases. I've tried to anticipate any questions. So when you're looking at the lesson 2 worksheet that I've given you, if you think there's too much explanation, you've got to remember that I'm trying to cater for every single student in the group. Anyway, again, just read through the notes, use this video to help sort of back up your knowledge and your current understanding. And as it says there, if you don't understand anything, just ask me for some help. Okay, a quick recap of what you should have brought through from lesson 1 and from year 1. All the definitions. I'm not going to go over this again. You need to keep using the definitions right throughout this unit. They will really help you if you get stuck on certain questions. Using the definitions, recalling them, writing them down, unpicking the definitions will help you a lot when it comes to certain questions. And ideally you should have already completed the work, looked over the notes that I've provided already, so you use this video as a recap. It's not essential really, but it's preferable. Okay, so we're going to look at Born-Haber cycles. I've gone into a lot of detail in the document with this, but we'll skip through them quite quickly now. As I say, this is a recap. So we're going to look at sodium chloride, basic, most familiar ionic compound. You've seen this from GCSE, even earlier, probably Key Stage 3 onwards. So that will be the enthalpy of formation, or what we're looking at there is formation, because we've got 1 mole of a compound being formed from its reactants in the standard states. So what I like to think about is that before you can form an ionic compound, you've got to get the ions ready to react. So to get the ions ready to react, you need to think about the metals first, then the non-metals, and you need to look at the form or the state that the metals in, the non-metals are in, right at the start of the reaction. So if we just went directly to the product, the sodium chloride, as a solid lattice, that would be the enthalpy of formation. We have a drop down in the enthalpy because it's an exothermic process, because it's formation. So that shows you the enthalpy of formation. But we can think about it in distinct stages. So this is covered in lesson 2, that we basically consider the metals first and then the non-metals, and we need to just basically get ions ready to form the lattice. So if we're making the ions from the metal first, we would look at, let's see, there we go, atomization. Remember that in the Born-Haber cycle, only one thing will change at each stage. So we've got solid sodium forming gaseous sodium, so we've got atomization there. The chlorine stays the same. Once we've got the atoms of sodium formed, we can then form the ions. So we've got the first ionization enthalpy for sodium there. So we go from sodium atoms to Na plus ions. Again, the chlorine stays the same, but you'll notice that we've got electrons being formed too. The next stage, because we've got the sodium ions ready to form the lattice, the next stage we focus on the chlorine. So we've got chlorine molecules there, Cl2, but we've got half a chlorine molecule. and we just form chlorine atoms. So again, that's atomization. So that's fairly straightforward. The next thing, we've got the first electron affinity for chlorine. So this is an exothermic process because there's attraction, or forming a bond, for want of a better word, between the electron and the positive nucleus in the chlorine atom. So all of these processes that we've looked at initially, atomization, we're putting energy in to break up the lattice. Atomization for chlorine, we're putting energy in to break up the molecule. They're endothermic processes. Ionization energy, again, we have to put energy in to overcome the attraction of the electron for the nucleus. And then the last thing we consider is that we've got our ions ready, and as soon as we've got our ions ready, and here they are, they can then form the solid lattice. So this would be the enthalpy of lattice formation. We're going to look at some calculations now. There's two methods you can use. I'll show you method 1 first and then method 2. Method 2 is my preferred method, but you just do it however you want. The mathematicians will probably get onto this quite quickly. So I've put the values in here. So these are fairly straightforward. You'll either be asked to construct a Born-Haber cycle, so they'll give you an ionic compound and you have to construct a complete Born-Haber cycle, or you know, finish off a partially completed one, and you will then almost certainly be asked to do a calculation. Now the calculations are relatively simple. You'll have 6 or 7 things that you need to consider, and they will give you 6 out of the 7 or 5 out of the 6 things to consider. So you will have most of the values. You only have one value that you need to calculate. So the maths is relatively simple. So what we have to consider is that if we've got an unknown enthalpy of lattice formation here, we've got a drop in enthalpy from the ions to the solid lattice, and we have to calculate that. But if you remember that we can use Hess's law, that we know that the overall enthalpy change is going to be the same regardless of the route taken. So what they're saying is that we can think about this enthalpy change going from the ions to the solid lattice. It's going to be the same value as going from the ions back across and down, if that makes sense. So it's just like an expanded Hess's law cycle that you've seen in year 1. It's just that there's a few more figures, but essentially the process is the same. So if we are going in this direction, we just need to make sure that all the arrows line up. Now you can see that we've got arrows that don't line up, so we're pushing up initially on the right hand side and then down on the left hand side. So we need to reverse this arrow initially for the enthalpy of electron affinity, and if we reverse the arrow, we've got to reverse the sign. So that goes from -349 to +349. Over the other side, we've got arrows again that are going against the direction that we need to consider. So we spin that arrow around, point it in the opposite direction, and the value changes. It goes from +122 to -122, and you keep doing the same until all the arrows are lined up in the correct direction, and all the values are changed. So we've got now negative values on the left hand side because we're pushing back. And then all you need to do is add all of these values up. So we've got the 349 -122 -496 -107 and the -411. If we add all them together, we will come out with -787 kilojoules per mole. So the 787 kilojoules per mole is basically our enthalpy of lattice formation. It's negative because it's an exothermic process. It's exothermic because it's bond forming. The clue's in the definition. It's the enthalpy of lattice formation. Method 2, I think it's easier because it allows you to consider slightly more complex examples that you would see in exams, but it also forces you to think about the sign that you're going to use in your final answer. In an exam, you might get confused. You might get confused with the maths. You haven't got time to be confused. So the final check that you would do, and I'll go through it when we approach it, the final check is that you consider whether bonds are being made or bonds are being formed, bonds are being broken. And if bonds are being made, it's exothermic. So the value should be negative, and if bonds are being broken, it's endothermic, so the value should be positive. Anyway, what I need to think about is splitting the Born-Haber cycle up into 2 parts, and I'll have an endothermic left-hand side and an exothermic right-hand side. And this is the way I think about it. As I say, I think it's a little bit easier. So all I need to do is make sure that we start off at the bottom, sort of the ground level, and we go up as far as we can with endothermic processes, and that will be equivalent to the drop down on the exothermic side. So if you've seen the notes, you would have seen the example of the students and the wall that he was trying to crawl across. Anyway, let's have a quick look. So I need to reverse these this arrow at the bottom, really, because we can see that this arrow is going in the wrong direction. I want to push up from this lower level, from the lowest level, the sodium chloride lattice. I want to push upwards with that, so I just need to reverse that. So if I reverse that arrow, make that an endothermic process, so i.e. energy going in, so that minus 411 becomes plus 411. And then I just add up everything on the left hand side with the understanding that it's going to be equal to the right hand side. So if I add all of these things up, 122, 496, 107 and 411, I come out with 1136. And I know that 1136 is going to be equal to the value of the figures on the right hand side. So we've got 349 plus our unknown is equal to 1136. You just rearrange. It's a simple rearranging task, where we've got 1136 minus 349 is 787. Now you notice that this doesn't give us the sign. This doesn't tell us whether it's positive or negative, so i.e. exothermic or endothermic. We have to consider, well, what are we looking at? We're looking at the enthalpy of formation. Now formation is going to be negative because it's an exothermic process. So because again, the clue's in the title, so it's going to be negative 787. I think it's better because sometimes they ask you to consider the enthalpy of lattice dissociation. If you do lattice dissociation, you're breaking the lattice up to form the ions. Now if you're breaking it up, then that would be a positive, an endothermic process, but it would actually be endothermic to the same value, 787. I think that's easier. Okay, a couple of things to remember. I've covered these in lesson 2 in your notes. 2 plus ions, 2 minus ions, a second ionization energy or second electron affinity. So you need to consider that. You also need to consider that in terms of any calculations that you do. And then checking the formula. So you need to make sure that if you've got, say like, the chlorine's a good example, because usually you see the enthalpy of atomization for chlorine, it's half a mole of chlorine molecules producing 1 mole of chlorine atoms, but sometimes you need 2 moles of chlorine atoms, so you would need to use double the number of molecules, so you need to use a whole mole of chlorine molecules. But if you do that, it would produce 2 moles of chlorine atoms. And when you produce 2 moles of chlorine atoms, that's obviously double the quantity that's stated in the definition for the enthalpy of atomization. So you're not producing 1 mole, you're producing 2. So the value that you put in is going to be twice the enthalpy of atomization. Have a look at the questions. It should become a lot easier when you start to do the questions. When you start to practice them, you'll hit a few bumps in the road, but they'll eventually iron themselves out as you see the type of questions that I'm talking about. Okay, that's the end of that lesson. So what you need to do is try those questions in the question pack that I've provided for you, and again, just ask me if you need any help.